Our next speaker is Dr. Joseph Michalski. He's of the Laboratory for Space Research at the University of Hong Kong.
How's it going, everyone? Really awesome to be invited to speak with you. My plan is to speak with you for about 20 minutes or so, but maybe a little bit longer. But I just want to tell you in advance that I'm really flattered to be invited to speak with you. I haven't been that engaged with the Mars Society for a little while, but I was a very eager member in the early days, late 90s and so on. And it's about time to get more involved, I guess. So this is a great opportunity, a great launching point for that. This is a great launching point, and we can always stay in touch with each other by Twitter, and you can check out the webpage, clays.space, and so on. Whenever I give a talk, I always want to just mention that sometimes as you go through life, you know, you're a professor or you work with a company and you represent a team, and that's what I do. I represent this team, these folks, and so we work together, and a bunch of graduate students, postdocs, and so on work with me. I couldn't do anything that I do alone, and so I just want to acknowledge that and say thanks. And also, we have some industry partners. Astro Reality is a pretty awesome company operating out of the Bay Area, and we work with them on space-related educational endeavors, and that's their main passion. So I would encourage you to check them out. DMEP, we work with them on remote sensing studies and so on. So we're a lot of, I guess the main point is that we're working together with industry to carry out research and to explore Earth and Mars together. One thing I like to point out sometimes is my background, and it's not necessarily to be so self-indulgent, but I guess what matters to me is that there would be many of you out there who might be in the high school age or university age or even younger, potentially thinking about what is my pathway to become seriously involved in space exploration. I take that to heart because I was that person. I grew up in Cleveland, Ohio, in the rural area, actually, not necessarily in Cleveland itself. And I had no idea that you could actually make a career out of this stuff. And that's why I just want to mention this very briefly so that if it connects with any of you out there who think, what's my pathway in? The answer to you is there are many, many pathways. Okay, there's not just one. You don't have to have a predetermined scholarship to Harvard or Oxford or something. It doesn't have to be that way. You know, I started off at a community college. I went to a state school in Ohio. I grinded my way through and made it to grad school and then on to JPL and worked with the French and UK space agencies and the Natural History Museum in London. Now I'm in Hong Kong. And so there are many pathways to whatever your version of success is. And I want you to feel inspired by that and to think creatively about it, what might work for you. That's all. So lastly, we're talking a little bit about Chinese space program. Now, most of this talk is about Mars science, to be honest, but nonetheless, I just want to be really clear that I'm not speaking on behalf of the CNSA, and I'm not an insider there. I don't work for them. They wouldn't want me to be telling you what they're doing because they honestly don't reveal a lot of their details to anyone. So I'm physically closer to it all here. Hong Kong is part of China, and I'm part of China. So I'm close to the action in a sense, but I'm speaking for myself, and I just have to be clear about that so that nobody who's working at CNSA, I don't want them to feel offended in any way. Most of you are aware of how we study Mars. How do we gain information? Well, we can use remote sensing, satellite images, telescopes, and so on. We can study meteorites that have landed here that contain chunks of Mars. Of course, those things are lacking context, and we don't really know where on Mars they came from. We can study Mars through surface operations, landed missions. We can do analog studies, go to the most remote deserts on Earth, or places like Iceland that are quite exotic and unusual, or Antarctica. We can study analogs. We can also use theoretical models to understand Mars. I personally tend to use remote sensing data the most. And that means that we look at reflected sunlight, the infrared portion of the sunlight largely, or emitted radiation, heat radiation. You can take the emitted heat and process it into something called emissivity, which gives you mineralogy information. We also can do active remote sensing. That means bouncing radiation off of the surface. In this case, laser altimetry. All the great topographic maps you see of Mars, those were made using laser altimetry. And so that's what I do. And it's really exciting because this is an amazing time to be a scientist or any member of the community exploring Mars. How cool is it that right now we have more active missions than we've ever had on the surface or in orbit. And we have real, legitimate, major involvement from the private sector. Now, you know very well, this isn't a new thing. The president of Mars Society, I believe, worked with Lockheed or Martin Marietta early on, and there have always been these huge contracts with private industry. So that's not a new thing. But I guess what's going on now, what's really exciting is that the involvement is legitimate and it's moving the needle. We're seeing pressure, and we want pressure. We want pressure on each other. We want positive kinds of tension and pressure, so that we can push each other, so that we can push government agencies, space agencies to do more. And I think that's the role that China plays as well. I don't want to speak too much about how things actually function within mainland China, because I'll be honest with you, I actually don't speak Mandarin and I don't read Chinese language. And it would be wrong for me to pretend that I understand so much. I don't. But I've worked a lot in mainland, and there are the boundary between what is private industry and what is government is not as obvious as what you have in other models. But mainly the thing for me is that China itself will make bold decisions. They've sent the first ever combination of orbiter and rover together and successfully done it. They pulled it off. It's amazing, and they're both operating flawlessly. So that's super cool, and that creative spirit and competitive energy is good for the world overall. Zhurong is now on the surface of Mars. Here's a sort of family portrait of Mars rovers. You can see that Zhurong is a solar-powered one, about bigger than the Mars exploration rovers, sort of like Curiosity rover size. And remember that solar-powered rovers, as opposed to nuclear-powered, right? You have two options, solar or nuclear. And solar-powered ones depend, of course, on the sun, and they need to be dust-free on the solar panels to operate. Now, what happened with the Mars exploration rovers? Those were launched by NASA in 2003, landed early 2004. One operated for about 7 years, and one for, I think, what was it, 14 years or something? The Opportunity rover. So the reason those were solar powered, and they were able to do it because they had the solar panels cleared of dust by dust devils, meaning little mini Martian tornadoes that clear off the dust. So it remains to be seen whether Zhurong will have similar luck in that regard. We don't know. It's landed in Utopia Planitia. So when you look at this image, what do you see? It's a pretty unusual landscape, right? These giant fractures. This is not the actual landing spot itself. This is just representative of Utopia. It's a cool image. That's what I'm showing you. This is from the HRSC instrument, German built and run on the Mars Express spacecraft. So these giant polygons are indicative of ice in the subsurface. So the details of exactly how much, where, what depth, all those things are for scientists to debate, but it's pretty clearly formed from ice. One of my students, Bin Long, he has written a paper about the landing site. And although this isn't necessarily a science conference, I just want to point that out. This is something that's out there and recently published. So we're just talking about what's available to the Chinese rover Zhurong in Utopia. What can we explore with that spacecraft? So that's the location. I don't know if you can see my pointer. And here is the place from orbit. And here is an image released by the CNSA showing the landing region. So the cool thing about it is that you have a bunch of different landforms to explore. Among them are these weird cones. The cones are effectively like they look like a cinder cone. I don't know if you've been to Sunset Crater in Arizona near Flagstaff, or maybe you've seen these in other places. They look a bit like volcanic cinder cones, but there are some differences, and when you look at them in detail, they actually seem like they might be potentially mud volcanoes, not actual volcanoes. So I'll come back to that in a moment, but that's a big difference. Now, this is a selfie taken by the rover. It dropped the camera down and backed away and took a photo of itself. How cool is that? I guess surprised nobody has thought to do that before. The confluence of technological capability and awareness. This is a great move, interesting and breathtaking to see like a selfie view of these robots operating on Mars. The rover has traveled over 1 kilometer already. As has been mentioned already in this conference, Mars is in conjunction right now. So that means you can't communicate with the robots over there very easily. And that's the case with Zhurong. So it's chilling out at the moment. And once we come out of conjunction, we'll get to operations again. But it's important to note that the mission has already been a technical success, has driven over 1 kilometer. And the pace at which this rover travels is faster than what the NASA rovers typically do. Now, I've worked with rover teams, and the balance among the team members, the engineers, and all that, it's really comes down to what are you trying to accomplish, how quickly, how do you have to give up the desire to measure rocks in situ at the expense. If you wish to travel quickly, you have to give up some of the observations you wish to make. That's the point I'm trying to make. So this rover has been cruising along, and it could go faster, could go slower, depending on how much detail you want from the individual spots. But you can see that it's been able to measure light-toned dunes and interesting soils, rocks, and so on. It's a cool site. From Bin Long's paper, here he shows all the different types of landforms that are available that the rover might ultimately be able to visit, including these cones, fields of cones, polygons, and patterns of polygons, impact craters, knobs, mesas, and so on. This area should be pretty ice rich, and many of you, if you're still hanging on from earlier this morning, you heard Nate Putzig speak about ice on Mars. So obviously, with this particular crowd, I don't need to explain the importance of ice for us, people who want to go live and work on Mars and build businesses and so on. Ice is critical, and it's a strategic resource. So one of the interesting things that will play out in the coming years will be how do different nations deal with ownership of resources on Mars. I know this is covered by the Outer Space Treaty, and if you haven't read that recently, have a look. But generally speaking, nobody owns resources on another planet, but when they get processed by a nation, they become a different asset, so that'll be something that will be interesting. So that the ice itself is not, nobody owns that. But when it gets processed into a fuel, then somebody can own the fuel. So that'll be an interesting sort of point for discussion in coming decades. But this rover will map ice using ground penetrating radar from the rover itself. So that'll be exciting to see what, here's an example of what GPR, ground penetrating radar, can do. And so there just haven't been a huge number of data points yet. They haven't been released yet. So we don't know exactly what Zhurong has found, but the same type of technology has been hugely successful for the Chinese on the moon, not for ice, but for measuring the regolith. And the word, the most technical word would be discontinuity. You're looking for differences in reflectors in the subsurface. Those differences among the reflectors can be rock, soil, sand, buried ejecta, can be ice. So that's what they're looking for. In the area where the rover landed, it's kind of in a transitional spot between the polygonal terrain and the ones with lots of cones, pitted cones. So we don't know exactly why that is the case, but it's exciting to land in an area where things are going on. And one of the main points I want to make is that this area, it's ice rich and considered to be what we call permafrost. That means like a periglacial, near glacial in the high Arctic or in the Antarctic, similar to that on Earth. And we know that in those areas, as a function of climate change, and I'm not, obviously interested in having any debate about climate change being human driven or not. It doesn't matter to me. Climates do change, and that's a fact. So when they change, things like permafrost melt and sublimate, and you get collapsed ground and release of things from the subsurface. So that happens on Earth. This is an area in Siberia with huge amounts of collapse and melting of periglacial material or permafrost. We think similar things have occurred on Mars. Now on Earth, those things, they can release methane from the subsurface. Now, I'm not sure how aware everybody is in the audience, but there's a lot of discussion about CO2 as a greenhouse gas, and it is a greenhouse gas. But you know what's really a greenhouse gas? It's methane. So on a side note, personally, when I see on the news one day it says methane has gone up for the 20th day in a row, that's when I start getting really concerned. That's a huge deal. And so it's a much stronger absorber and so on. So we think that was an important part for greenhouse warming on ancient Mars. We detect methane on Mars today occasionally in wispy transient measurements, but we don't know where it comes from. And it could come from melting of permafrost on the planet. It's one possibility. This is a complex diagram on the right side from the paper I told you about. I guess if you just look at this diagram, you see that the ground surface is here, and you have permafrost and frozen ground, and you have methane sources in the subsurface, and that stuff will get released to the surface due to melting of the permafrost or other types of activities. Now, does methane mean microbes? No, it could mean that. Measuring it doesn't mean there are microbes, but it's an energy source for microbes, and it could be a product of metabolism of microbes, and we can't rule those things out. So in fact, a colleague of mine, Jesse Tarnas, we wrote a paper led by Jesse in astrobiology recently about the viability of a modern biosphere in the subsurface of Mars. Pretty cool stuff. We know that the surface of Mars is bathed in radiation. It's super cold. It's hyper arid. It's ultra oxidizing. It's not a pleasant place. If you were a microbe, you wouldn't want to hang out on the surface of Mars. But the subsurface, yeah, maybe could. What do we know about the deep biosphere of Earth? Well, a lot. We're learning a lot. We've learned a fair bit in the last 20 years, but prior to about 20 or 30 years ago, we didn't know hardly anything about it. There's more life. If you were to put it on a scale, there's more biomass in the subsurface of Earth than the surface. Even with all the rainforests, even with all the people, all the whales, all the bugs, everything, more biomass in the subsurface. Amazing, right? So while there's an emphasis on surface processes, for Mars, people are obsessed with channels, rivers, lakes, for good reason. They're cool. And NASA will keep going for these environments. Perseverance has done that, and this is a great site, Jezero crater. It'll be interesting to explore. But the subsurface may be really where it's at. Mars, because of its lower gravity, it has more pore space. Just think about it. All the gravity pushing down on the ground compacts the Earth. With less gravity, there's less compaction, so there's more pore space. More pore space means the space between all the silicate grains where bugs can hang out, where water can be, where nutrients can be. And if you were to model this, which we've done, you'll find that all the goodies you need for life are there on Mars. We don't know that life is there, but in the subsurface, everything is there. So Mars is really important because it actually could contain the Holy Grail of how did geobiology become biology? How did you make the first cells? On Earth, if you look at the origin of life on Earth, going back from modern time to 2 billion years ago, 3 billion years ago, 4, the Earth's crust is not very well preserved. So it's hard for us to answer how did life form? We don't know. We have some ideas about different hydrothermal environments and so on. We have some concept of when different things evolved, like when did the first cellular life occur, cells with nucleus, when did photosynthesis occur, all that stuff. But the crust, the actual geologic record, is not well preserved. And on Mars, it's much better preserved. So that's the key point. This is the most important thing about Mars. It's got a geologic record of the earliest important events. And if they didn't occur, if biology never occurred on Mars, fine, okay. Biology will occur on Mars when we go there. But whether microbes ever formed, we don't know, but we must go look. And I would argue that the key point is that not necessarily to find microbial life, although that's awesome and we hope that would occur. This diagram shows that even if I'm not sure if you can see my pointer or not, but you search for life on Mars, and let's say you're lucky enough to discover it, then you would quickly just answer, well, how did Martian life form? The same that you would ask on Earth. Well, what was the previous step? And then you get to searching for clues to abiogenesis. So I would argue, like, just skip these other ones and go straight to searching for clues to abiogenesis, the prebiotic chemistry and all that stuff that leads to life. So while NASA is always pursuing lakes on Mars and things like that, that's great. I mean, huge amount of respect for how NASA does things. There's another way to do stuff. And it could be that searching in the subsurface, not by drilling or anything, but to look where materials may be exhumed from the subsurface, that could be the way to go. And that could be one way for China to have an advantage, in terms of catching up in Mars exploration, to go to the most exciting places or to extract materials from fundamentally different types of deposits. Now, China's plans, they don't publish everything they plan to do, but what they've roughly said is that they expect to do a sample return mission in the late 2020s. It sounds horribly audacious to say, well, we'll just go do a sample return mission, but guess what? They've done it, man. They've already done it. It sounds audacious to say we're going to send a rover and an orbiter together in the same mission in our first try. We're going to pull it off. Well, guess what? They did it. So they said they're going to do this. They're going to go get a sample and just bring it back. While everyone else, NASA and ESA spent 20 years screwing around with the next rover and talking about sample return. NASA spent 50 years talking about sample return. Well, guess what? China's just going to go do it. So that's awesome to me. That's exciting. And to pretend that we know the exact details of how are, it's misguided. But what I would say is that they've done it with Chang'e 5, and brought the samples back from the moon. They know how to do it. And guess what? they've allowed scientists to apply for those samples, for those materials to be distributed for exploration. That's great. That's the way we want science done. So I'll leave you here. I'll leave you with this, and we can have some discussion if you wish. But that's my um, excitement for the future, is that China is really pushing the envelope, and NASA's great, European Space Agency great, India great, Japan. We have so many players now. Great, more better. That's what we want. Thanks.
Thank you, Joe. Anushka, do we have any questions for Joe?
Yes. So one of the questions was like, how can we erupt the moon on Olympus to increase its magnetosphere?
Oh, it's not the moon, Anushka. It's Olympus Mons, the volcano. Yeah.
Yes, sorry.
How can we erupt Olympus Mons for enlarging Mars's magnetosphere?
Well, okay, so to be clear, the mystery of Mars' magnetic field is one of the most interesting parts of Mars science. Now, what do we know about it? We know that it had a very strong magnetic field early on, and then we know that it's not there now. Those two things we know for sure. And you can measure roughly when it may have stopped, when the magnetic field may have stopped, by looking at something called remnant magnetism. That means the magnetic field gets stored within magnetic minerals in the rocks. And then the rocks form and they sit there for billions of years. So some rocks will have it, some rocks won't have it. And the boundary between the rocks that have it and the ones that don't have it is when the magnetic field shut off. So that was about 4.1 billion years ago from Mars, as far as we know. I guarantee you there'll be big discoveries in this area in the coming decade, but that's the number that we use. And there's no way to turn it back on. And that's going to be the problem for humans who want to go create a society on Mars, because the magnetic field on Earth protects us from solar energetic particles and some forms of cosmic radiation. So not having it on Mars is problematic, and there's no way to turn it back on. That'll be something we just have to deal with.
Okay, any other questions? Looks like
There's
one in the
another
Q&A.
question. Yes. That is like, what drew you to do research at Hong Kong University? So is that research environmental? Is the research environment or CNSA's ambitious goals?
Well, if I didn't understand the question, you can correct me. I'll give a short answer, and then you can tell me if I did not understand. At University of Hong Kong, I'm a geologist, and so I study the Earth and Mars. Most of my research is on Mars. We're interested in many different aspects of exploring Mars, mostly to do with understanding how the planet came to be geologically. But we also do some applied research. I have a postdoctoral candidate who's doing 3D printing with clay minerals. So clay minerals, the things that you make pottery from and so on Earth, the clays exist on Mars. Now they're important for lots of reasons. They're important for understanding climate and preservation of ancient life potentially, but the clays themselves are a resource. You know, they contain water that can be extracted, and they are also it can be used for 3D printing. So one of the things we're doing is trying to figure out how to do that from Mars.
Okay, thank you. I had a personal question. So have we found any similarities between Mars soil and Earth soil?
Yeah, there are a lot of similarities. One of the effectively what you find on Mars is basalt which is like the kind of rock you have in Hawaii or in Iceland. And so it's a dark volcanic rock, and the soil that forms from it is ground up volcanic stuff. The word soil, by the way, on Earth is problematic because soil on Earth is always mediated by microbes, always. So that's why you hear scientists sometimes say regolith, because regolith is a more boring but more accurate term. There's regolith on the moon, there's regolith on Mars. We can't, for somebody who studies soil, they would be maybe offended if we said there's soil on the moon, because there are no microbes to facilitate some of the chemical processes and so on. But other than the microbe part, the comminution of the volcanic material into volcanic particulates is very similar to what we see on Earth. In fact, I have a mate named J.R. Skock who runs a company called Made of Mars, and he's looked at ways that you can take volcanic material and process it into products for that humans might want. So check out Made of Mars.
Okay, great.
Hi.
Go ahead, Jay. Alt space VR, go ahead.
Can you comment on the work of Dr. Gil Levin?
Can you explain it again?
Oh, Dr. Gil Levin, the one who made one of the life science experiments on the Viking lander?
The
Okay.
labeled release experiment on the Viking lander that had signals, the positive signals for life. It's a little bit of a controversial experiment. Can you tell us anything about your thoughts on that?
I will do that as long as you put your mohawk back on the screen, because I was very taken with that. Yeah, that, I mean, those, my best understanding of that suite of experiment, yes, is that the Martian surface has an unusual suite of oxidants that weren't predicted ahead of the Viking experiments. Now, because as Carl Sagan had said, like, exactly what he say is that major conclusions must be met with substantial evidence. The evidence is consistent with metabolism, but it's also consistent with there just being hyper oxidizing material. So that's the bottom line, is that it's inconclusive in those regards. We didn't know there were all these perchlorate and weird chemical compounds on the Martian surface that are so oxidizing. And so that experiment wouldn't be designed the same way today, and it's not conclusive as a result. That's the end of the answer.
Thank you, Joe.
Okay, thank you. So the question was like, he wanted to know what is the research culture in HKU, like how is it compared to US or Europe, and what?
That's not. What is the research culture like?
I think he's asking, do you find that the research culture in Hong Kong and China in general, is it more ambitious compared to, say, the US or Europe? And is that why you work at Hong Kong U?
Oh, well, no, I don't think it's better or anything like that. I just work here because I just chose to do something exciting. But there are advantages and disadvantages. Advantages would be that there's a huge trajectory toward space exploration in China, obviously. And Hong Kong itself, to answer your question, I'm sorry, I don't want this to be boring, but Hong Kong itself doesn't see itself as the city, and the city itself doesn't see itself as a spacefaring technology-driven part of the world, but that is changing. So, and I came here to help be part of that change. Now, I guess the truest answer is that we'll see. You know, it's a period of immense change in Hong Kong in a lot of ways. And some of those things are exciting and some are less exciting, but research will be one of the areas that I think will maintain and become stronger because China is very invested in science. So what I think what happens in the States, for example, I am American, so sometimes I speak freely about American culture. Forgive me for that. The anti intellectual behavior that occurs in the States is astounding to me, and we don't see that here.
Okay. Well, on that note, I think we're going to go ahead and end the evening. Thank you so much, Joe, for participating in our conference. We really appreciated your remarks, and thank you so much.
So thanks, everybody. Thanks, James.